So in this video, we're going to try and solve for the transfer function g, which is equal to omega divided by t. Omega is the speed that we're measuring at this point on the shaft, and t is the torque that's applied to it, and it's drawn in here. So let's start by drawing the free body diagram. I'll write of J, but it's really the only one we're going to have to analyze. That's because we've only got one inertia sitting in our system, and we don't have any extra components that are in series either that are going to need the extra free body diagrams as well. So there'll be another video looking at that situation. This one's really simple though. Taking out just our component of interest here and drawing the forces onto it. So we're going to have the torque that's applied to it, and we can see that that's drawn in this direction. That's T. And we can put our inertia term on. So we know that by applying this torque, we're going to cause rotation of our shaft. I'm going to assume it's the same direction. And it's going to be equal to J, the size of the inertia, multiplied by theta double dot. So this is the angular acceleration. Remember, in like a spring mass damper system, the inertia part is the mass times the linear acceleration. So this one is just our inertia times by the angular acceleration. So resisting this motion, we're going to have our spring and our damper. So if we start with looking at the spring, it's going to try and pull us the opposite direction. Okay, opposite this direction of motion. And the size of it is going to be K multiplied by the angle that it gets pulled at. So since it's butted up against a wall, the angle of the spring is just going to be the same as what's the shaft's at, so theta. So now we need to consider the damper. Again, it's going to oppose the direction of our motion, so it's going to go back, and it's going to be equal to d times theta dot. So this is the speed that the shaft is going at. Again, because it's butted up against a wall, this one has a speed of 0 at the wall. So now we can go ahead and apply the equation that we need to satisfy, and that's the sum of the torques have to be equal to J theta double dot. And I'm going to assume this direction is positive. So we're going to get T minus, it's going the other way, D theta dot. This is also going the other way, so it's minus K theta. And then the right hand side relates to this term here, which I've dotted in. And it's in the positive direction, so it's positive J theta double dot. So let's go ahead and put everything onto the other side of the equation. And we end up with that. And now what I want to do is Laplace transform it, so that's why we put the s's into it. So t is a function of time. This is the torque that's being applied, so it could change over time. So when we Laplace transform it, it just essentially becomes itself. You would capitalize it, but I've already drawn it in a capital, so we'll just ignore that. J is a constant, so that stays out the front. And theta we know is a function of time. So Laplace transforming it, because it's got two dots, it gets two s's, and we leave the theta on the end. Again, you would capitalize this, but it's theta, so I won't bother. D is a constant that stays out the front. Oop, this one is going to get one s because it's got one dot, and this one, K is the constant, and this just becomes itself. I should quickly mention that we're going to assume that everything starts in its like equilibrium position. There's no initial displacement, no initial velocities, anything like that. Otherwise the Laplace transform would be slightly different. So now what I'm going to do is I'm going to factorize out theta. And this is what I'm left with. And now what I want to do is change this into the form theta divided by t, because that's very similar to omega divided by t, the transfer function I'm going for. So theta on t. So this goes down, this goes down. Okay. Now the only catch is, rather than getting theta on time, I want omega on time. And omega and theta are related together through the derivative. So omega is the same as theta dot, the derivative of theta with respect to time, i.e. the speed, angular velocity. So if I wanted to Laplace transform this, it would be the same as theta s. So what I can do is, if I can make this look like theta s on the top line, I can just, sub it straight out for omega. So if I multiply both sides of the equation by s, I'm going to have that situation. So this here becomes omega, t remains the same, and I'm just going to end up with an extra s on the top line for the transfer function. So this here is my answer for relating those properties together. So that's all there is. See you in another video.